Hi, my name is Brian Caffo, and this is Lecture 2 of Mathematical Biostatistics Boot Camp. In the last lecture, we covered probability and the basics of biostatistics at a very conceptual level. In this lecture, we're going to get much more down to specifics. First, we're going to cover the subject of probability, which are mathematical functions. So we'll talk about the specifics of those kinds of mathematical functions. Then in 2, we'll talk about random variables. Random variables are just like any other variables that you've maybe encountered before, like in calculus, with the exception that they are random. They can take lots of different values. In section 3, we're going to talk about probability mass functions and probability density functions. These are mathematical functions that map probability to random variables. In section 4, we're going to talk about so-called cumulative distribution functions, CDFs, very associated things called survival functions, and quantiles. And then we'll wrap up with a brief summary. So a probability measure is the function that is going to govern the rules of probability for us. And there's basically 3 rules that a probability measure has to follow. And these 3 rules, and every probability textbook will give you these 3 rules or things that are equivalent. There's an interesting history behind these 3 rules. The Russian mathematician Kolmogorov, who's generally considered the father of all of modern probability, basically distilled everything that we thought of as in terms of things that a probability should have to follow. He minimized them down to the minimal set of rules that you could possibly have. If you delete any of these rules, you wind up with something that fails in some fundamental way to be probability. And if you add any other rules, they turn out to be excessive. So it's really kind of an interesting collection of research he did. It's also interesting to note that Kolmogorov tried to do something else, which is to figure out what exactly it is we mean by probability. So he found that problem to be very hard, and I think if you look into it, the theory of exactly what is randomness and exactly what is probability measure is a very deep problem, and philosophers are still debating this, and I question whether or not it'll ever reach a resolution. However, one thing that's much less controversial is what rules probability has to follow, and Kolmogorov just nailed it. It's done. So let's go over these 3 rules. So a probability measure P, the letter P here in italics, is a function that maps events, which are subsets of the sample space, to numbers between 0 and 1. That's item 1 here. So events E have to be mapped to numbers between 0 and 1. So a probability is a function that operates on sets. The second item here says that the probability of the whole sample space has to be 1. Basically what this means is that something has to happen. The sample space has to enumerate everything possible that can happen. So for example, if you're flipping a coin, the coin can either be heads or tails. If the sample space is heads or tails, when you flip the coin, one of those 2 things has to happen. The probability of one of them happening is 1. The coin can't land on its side. If you want to allow for the coin to land on its side, then it has to be heads, tails, and land on its side as the sample space. The third statement, and we'll talk a lot about the third statement because we're giving you an incorrect version of it. The third statement says that if 2 events are mutually exclusive, and recall events are mutually exclusive if they have no intersection, if 2 events E1 and E2 are mutually exclusive, then the probability of the union is the sum of their probabilities. So as an example, we just talked about coin flipping, and we said the probability of a head or a tail has to be 1. The probability of either getting a head or a tail has to be 1. So let's talk about that in the context of Rule 3. If E1 is the event that you get a head and E2 is the event that you get a tail, then the probability of E1 union E2, the probability that you get a head or tail, winds up being the probability of getting a head, let's say it's 0.5, plus the probability of getting a tail, which is 0.5, which adds up to 1, exactly what we know it has to. So in part 3, the third rule that we talked about in the previous slide, I said that there was some concern over it not being complete. So I'm going to elaborate on what I mean by that in this slide. First of all, let's note the following fact. Part 3 of the previous slide, the fact that if you have 2 mutually exclusive events, the probability of their union is the sum of their probabilities, that pretty easily extends to the so-called finite additivity, that instead of having 2, if you had 3 or 4 or 5, or let's just say n events, that the probability of their union equals the sum of their probabilities. So in this case, I have the probability of the union of a collection of mutually exclusive events, AI, equals the sum of their probabilities. That pretty directly follows from the previous definition. Just to give you a sense of how it works, if you had 3 events, say A1, A2, and A3, and they're all mutually exclusive, then the probability of A1 union A2 and A3 is the sum of the probability of A1 plus the probability of A2 union A3, right? Because A1 is mutually exclusive from the union of A2 and A3. And then that second probability, the probability of A2 union A3, is then again the probability of the union of 2 mutually exclusive events. So it is the probability of A2 plus the probability of A3. And you can formalize this with mathematical induction if you want. So at any rate, the rule that I gave you implies so-called finite additivity, and it seems like maybe that should be enough to cover everything. Well, the probabilists have thought very hard, and they said, well, maybe we think it should be countable additivity. Instead of n, it should go up to infinity. And it's not the case that the definition that we gave implies countable additivity, that if you had an infinite collection of mutually exclusive events, that the probability of the union is the sum of the probabilities, which requires ideas of limits and other things that we're not going to cover so much in this class. So at any rate, it's the case that finite additivity does not imply countable additivity, but of course countable additivity implies finite additivity. So in standard probability classes, in the more theoretical probability classes, they make quite a bit of hay out of this distinction. They discuss it a lot, and the general definition gives countable additivity rather than finite additivity. If you take a more advanced measure theoretic probability class, they will deal with this issue at length. In this class, this will be the last time we discuss this. In general, finite additivity will work just fine for us. In the next slide, we're going to talk about more details about what the probability function operates on. And again, it's going to be a rather important but maybe unnecessary detail for this class. So we're going to, again, it's going to be another thing that we cover very briefly and then tend not to think about for the remainder of the lectures. Recall that our probability function operates on events, which are subsets of the sample space, and maps them to numbers between 0 and 1. So we need an appropriate domain of our function. Our domain is not an event, it's a collection of events. So let me go through an example to make this idea a little bit more clear. So let's suppose the sample space is simply the numbers 1, 2, or 3. Imagine somehow if you had a 3-sided die that you were rolling. Then the probability function operates on all possible events that are subsets of that sample space. So in this case, the null event, the event that you get a 1, a 2, a 3, a 1 or 2, a 1 or 3, a 2 or 3, or the whole sample space, a 1, 2, or 3. And this is fine. Pretty much whenever you have a finite set, the domain of the probability function will operate on all possible subsets of the sample space. In this case, we're using the letter script F to denote this so-called domain. When the sample space is a continuous set, it actually gets a lot harder. And you can no longer say things like the probability operates on the set of all possible subsets of a continuous set. And it turns out that that is an incredibly deep mathematical problem. The mathematician Cantor thought about measure and sets in a very deep way, and if you want to read about an interesting character in the history of mathematics, you should read about Cantor. He came up with interesting sets that, for example, you just can't reasonably include in the definition of a probability. So in this class, we're not going to think about this at all, but I wanted to raise it just for those students that go on to take some of these more advanced classes so that you'll be prepared for some of these admittedly kind of strange ideas that come up when you try to talk about this set of sets that probabilities operate on. For our purposes, When our sample space is a continuous set, we're mostly going to be concerned with things like intervals or unions of intervals. And in that case, the definitions are very easy. So our definition of the domain that the probability operates on, we're just going to assume that anything that we can think of, and since none of us are Cantor, probably we won't think of anything too crazy, anything that we can think of is just fine. And that definition will work really well for this class. In this slide, we're going to give a laundry list of properties that a probability function has to have by virtue of its three definitions. So you should find it kind of interesting that the three definitions then imply all of these things that we know probabilities have to have. So take this first bullet here. The probability of the null set is 0. Basically, the probability that nothing happens is 0. So if you say you're going to roll a die, you actually roll a die. If you say you're going to flip a coin, you actually flip a coin. That's basically what the probability of the null set being 0 is. The second bullet says the probability of an event is 1 minus the probability of its complement. In other words, for example, if E is the probability that you get a head when you flip a coin, the probability of getting a head is 1 minus the probability of getting a tail. And that's, of course, true on a fair coin where the probability of a head is 0.5 and the probability of a tail is 0.5. But let's suppose you have an unfair coin. Maybe you glued together a nickel and a US dime and made a funny shaped coin that you didn't know whether or not the probability of a head was 0.5. Let's suppose the probability of a head in that case was 0.3. Well, this would say if the probability of a head is 0.3, then the probability of a tail has to be 0.7. The next bullet says that the probability of the union of two events is the probability of their sum, and that's all we would have to say if the events are mutually exclusive, but we have to subtract off the intersection if they are not mutually exclusive. And the intuition behind this statement is something like this. When you add the probability of A, you've added the probability of A, which includes the part of A that intersects B and the part of A that does not intersect B. And then you've added the probability of B, which includes the part of B that intersects A and the part of B that does not intersect A. So you have then just added the part of A that intersects B and the part of B that intersects A. In other words, A intersect B, you've added it twice. Once when you added probability of A, once when you added probability of B. You've added it twice, you only wanted to add it once, so subtract it out. That's how the rule works. The next bullet point is a pretty simple point. If A is a subset of B, then probability of A is less than or equal to the probability of B. So this is analogous to saying if I'm rolling a die and A is, say, the event that I get a 1 and B is the event that I get a 1 or a 2, then the probability of getting a 1 is less than the probability of getting a 1 or a 2. And so this rule, I think, makes a lot of sense. From De Morgan's laws, we get probability of A union B is 1 minus the probability of A complement intersect B complement. The next bullet point is kind of along the lines of subtraction. So A intersect B complement, that set is sort of like subtracting B out of A, the component of A that has nothing to do with B. So the probability of A removing B is the probability of A minus the probability of A intersect B. So that works out to be a nice rule. That sort of set level subtraction works out to be equivalent to subtracting the probabilities. The next bullet talks about the probability of the union of events again. This says the probability of the union of a collection of events is less than or equal to the sum of the probability of the events. Now again, if the events are mutually exclusive, then the probability of the union has to equal the sum of the probabilities. So this rule doesn't violate that rule whatsoever, but it also accounts for the times when the events are not mutually exclusive. The final rule talks again about unions of events. In this case, the probability that the union of events is bigger than the probability of the maximum of the collection of probabilities. Again, this rule holds if the events are mutually exclusive or not. But there's intuition behind this that's very easy. The union is everything that's in any of the events, E1 to En, so it contains anything. The probability of that has to be bigger than any of its component events. I think that makes quite a bit of sense. So just let me give you an example. Go back to our die roll. If E1 is the event that you get a 1, E2 is the event that you get a 2, E3 is the event that you get a 3, the probability on the left-hand side of the equation is the probability that you get a 1, 2, or 3. On the right-hand side, it says that it's the maximum probability. If you're talking about a standard die, probability of a 1 is 1/6, probability 2 is 1/6, probability 3 is 1/6, so the maximum of them is 1/6. On the left-hand side, the probability of the union is the probability of a 1, 2, or 3, which is 1/2. So 1/2 is definitely bigger than 1/6. So let me give you an example of one of these proofs. So let's take a simple one. The probability of an event is 1 minus the probability of its complement. So consider line 1. Recall that the probability of the whole sample space is 1. But again, the sample space for any event is equal to the union of that event and its complement. So omega equals E union E complement. Then consider the next line. An event is always mutually exclusive with its complement. Something cannot simultaneously occur and not occur. So events are always mutually exclusive with their complement. So E and E complement are mutually exclusive events. So we can take the probability of the union and turn it into the sum of the probabilities. Probability of E plus the probability of E complement, and then that's simply a restatement of what we want to prove. 1 equals probability of E plus the probability of E complement. Let's do a more complex example of the consequences of the probability rules. So recall that we discussed that the probability of the union of a collection of events is less than or equal to the sum of the probabilities. And recall that less than or equal to is an equality if the events are mutually exclusive. So let's prove this using mathematical induction. The way mathematical induction works is you prove it for some small statement, 1 or 2, then you assume that it's true for, say, n minus 1, and then prove that it's true for n. That's how mathematical induction works. So let's consider just 2 events. Probability of E1 union E2. Well, that's by one of the other consequences of the probability rules that we investigated. That's equal to probability of E1 plus the probability of E2 minus the probability of E1 intersect E2. And here I'm assuming that we've gone ahead and proved that one as well. So this final term here that's subtracted off, minus probability E1, E2, we are subtracting off a number that has to be positive. Remember, probabilities have to be between 0 and 1, so they have to be non-negative at least. So if we throw away that final term, what's left can only get bigger, right? So if we're subtracting off a positive number and we throw it away, then it's got to get bigger. So then we've established the result for the case when we have 2 events. Now let's assume the result is true when we have n minus 1 events, and let's consider n events. So we want to demonstrate that the probability of the union of the EI is less than or equal to the sum of the probabilities. So let's write out the probability of the union of the EIs as En union with the union of the rest of them. So the union of the rest of them, I equal 1 to n minus 1, is a single set. We've already done that. That's just 2 sets, En, and the union of the remainder are 2 separate sets. We already worked it out for 2 sets. So we can say that the probability of the union E1 to En is less than or equal to the probability of En plus the probability of the remainder. Now consider the next line. In the next line, we have the probability of En from the previous line. And then we can say that we have only gotten bigger by our induction hypothesis, by the fact that we assume that this statement is true for n minus 1 events. So there, if we switch this probability from the probability of the union to the sum of the probabilities, we've only made it bigger, so we can maintain that inequality. Then just collecting the terms, then we just have that this is the sum of the probabilities. And just to give you a sense of the notation I use, when I write equals on this last line, I mean it equals the previous line, not that it's equal to the first line. So I'm assuming that it's less than or equal to, less than or equal to, and equal to, implying that the final statement is less than or equal to the first statement, but equal to the previous line. So that's notation that I commonly use. So you should be able to prove all of these probability statements that we outlined on the previous slide. This particular one, let's go ahead and take a step back from the mathematics and try and put some of this within a context. So the National Sleep Foundation reports that around 3% of the American population has sleep apnea. This is a sleep disease where the upper airways collapses. They also report that around 10% of the North American and European population has restless leg syndrome. For the purpose of our discussion, let's just assume that this is 10% of the American population has restless leg syndrome. Similarly, they report that 58% of adults in the U.S. experience insomnia. So imagine if you were a sleep physician and you wanted to know the probability that a random American has any of these three sleep disorders. Can you simply add these three probabilities, 3%, 10%, and 58%, and get 71% of people have at least one of these sleep problems? So this question is nothing other than a restatement of the probability relationship that we just proved. So here I'm using A instead of E, but maybe that's a good thing to do just so you get used to not using the same letter for everything. So let's let A1 be that the person has sleep apnea, A2 be the event that the person has restless leg syndrome, and A3 be the event that a person has insomnia. And I'm going to gloss over the details, but the probability that a person has at least one of these diseases is, we're talking about the union, A1 union, A2 union, A3. So we want to know the probability of the union. Well, that's only equal to the sum of the probabilities, right, when A1, A2, and A3 are mutually exclusive. Otherwise, it's the probability of A1 plus the probability of A2 plus the probability of A3, and we have to subtract out other things. And in this case, I give you the exact equation for relating the probability of the union of three events to the probability of A1, A2, and A3. And so it works out to be 0.71, but then there's all this other stuff. The A1 intersect A2, A1 intersect A3, A2 intersect A3, and then you have to add in the triple intersection, A1 intersect A2, intersect A3. And I would suggest you go through and figure out why exactly it is this formula works out. But the point is that other stuff is non-trivial, and it's always there unless A1, A2, and A3 are mutually exclusive. And so you can't simply add these other things. And in fact, in this case, from a scientific perspective, I mean, we're talking about it from a mathematical perspective, but from a scientific perspective, it's probably the case that there's a non-trivial intersection of people with sleep apnea and restless leg syndrome, and a non-trivial intersection of people with restless leg syndrome and insomnia, and so on, so that probably this 0.71 is not close at all. So that ends our whirlwind tour of the basics of probability mathematics. Next, we're going to talk about random variables. So welcome back, recruits, to Lecture 2 of Mathematical Biostatistics Boot Camp, and now we're going to talk about random variables. So random variables, as the slide says, is simply a numerical outcome of an experiment. Random variables are just variables, like you see in calculus, but they have probability distributions associated with them. We're only going to talk about two kinds of random variables, discrete or continuous random variables. Discrete random variables are any random variables that can take just a countable number of possibilities. So even if it's infinite, if you can enumerate the collection of values that a random variable can take, it's going to be discrete. So what I mean by even if it's infinite, if you have a random variable that is the number of people that show up at a bus stop, well, I suppose there is a theoretical limit to that, but it might be useful mathematically to model that as if that count can go all the way up to infinity. But the point is that we can count them. We can count one person, two people, three people, four people, and so on. If the random variable can take any possible value on the real line or a subset of the real line, then we'll call the random variable continuous. And we'll have to have a slightly different treatment of continuous versus discrete random variables, but I think when we go through it, we'll try to draw the similarities between how they're treated. This list of random variables either being discrete or continuous is non-exhaustive. You can actually have a random variable that is both discrete and continuous. To give you an example, let's think of a good way to generate a continuous random variable, or something at least that could conceptually be viewed as a continuous random variable. Suppose you were to draw a line on a piece of paper that goes from 0 to 2. You label one end of the line 0 and another end of the line 2, and then you drop your pencil and it hits a random point in between 0 and 2. and you were to measure the distance between 0 to 2, how far that point is. Well, maybe you can argue you can only measure to so fine of a scale, but let's forget about issues like that. Honestly, you would model this as sort of a continuous random variable. That distance you can measure to several decimal places, and so we'll think of it as sort of a continuous one. So let's think about how could you possibly generate a random variable that's both discrete and continuous. Well, let's suppose, so we have our little experiment where we can generate something that's continuous or continuous enough for us to think of it as continuous. And then we have another example, say just rolling a die that generates 1, 2, 3, 4, 5, 6, clearly generates a discrete random variable. Suppose then you were to flip a coin, and if the coin comes up heads, you use your pencil to get this continuous random variable. And if the coin comes up tails, you use this die to get your discrete random variable. Well, the resulting random variable could have possibly been continuous, or it could have been discrete. So that random variable, if we were to describe its behavior, we would have to describe it as potentially being both discrete and continuous. So we won't deal too much with random variables like that. I would add that they're not entirely useless. So let me give you an example of a random variable that's kind of both discrete and continuous, but is used in practice. So imagine if you're looking at expenditures of some sort. Let's say you were an insurance company and you were looking at how much you had to pay out in terms of insurance. Well, for some people that never got sick, you paid out 0. It's a discrete number, exactly 0. For everyone else, you may be paid out a certain amount, and that remainder would probably be best modeled by a continuous random variable because you have to account for it down to the fraction of a penny or something like that. So in that case, if you're the insurance company and you're evaluating the distributional behavior of expenditures, you might want to model that with a random variable that can both take the discrete value 0 and can take the continuous values for all expenditures beyond 0. So at any rate, this is a long-winded discussion of random variables that we're not going to consider in this class, ones that are both discrete and continuous, but I just wanted to raise the point that the kinds of random variables that we're going to describe are non-exhaustive. Let's go through some simple examples of variables that can be thought of random variables. So if you flip a coin, the head or tail 0 or 1 outcome of a coin flip is clearly a random variable. If you roll a die, the 1, 2, 3, 4, 5, 6 outcome from rolling a die could be modeled as a random variable. And again, I should say could be modeled as a random variable. If you say it is a random variable, then you get into this discussion of, well, is a coin flip really random? Maybe if you knew exactly how much pressure the person applied to the coin and all. We're not going to worry about that kind of extremely conceptual thinking in this class. We're going to say practically we'd like to model a coin as random. Practically we'd like to model a die as if it were random. But practically we'd like to model lots of other things as if they were random too. So for example, if we have a random selection of subjects and we take their body mass index at baseline and then take it 4 years later, we might want to model that change in BMI or the BMI after an amount of time as being a random variable. Same thing with hypertension. We might want to model their hypertension status, whether they have hypertension or not, as a random variable. And this latter point also reminds us of why coin flipping is very important. Coin flipping seems like a trivial random variable, but it forms the basis for a lot of analysis. We think of a lot of things as if they were coin flips. So we might model, for example, the prevalence of hypertension. We might think of the data going into that modeling as if they were a bunch of coin flips. And the idea of a coin flip will help conceptualize the model that we're formulating. So we've described some examples, some very basic examples of random variables. So what we need is a mathematics of random variables to use them. And we have a mathematics of probability. And we've acknowledged we're at least willing to think of kinds of variables as if they're random. We'd like to put those two ideas together. So we need functions that map the rules of probability to random variables. And so for discrete random variables, the kind of functions that we're talking about are so-called probability mass functions. So a probability mass function is simply a function that takes the values that a random variable can take and maps it to their associated probabilities. So for a die, the probability of P of 1 would be 1/6, for example. And it turns out quite a few functions satisfy the definition of being a probability mass function. In fact, you only have to satisfy 2 rules if you'd like to be a probability mass function. The first rule is that you have to be bigger than 0 for all of the arguments, where here x is the collection of possible values that a random variable can take. And the second rule is that if you sum over all possible values, then you get 1. This is just exactly analogous to our probability statement that the probability of the whole sample space has to be 1. But here we've put it in the terms of a probability mass function. I want to talk a little bit about this notation. Notice here I have this small x, and when we defined random variables 2 pages previously, we used a capital X. So this is very common and maybe slightly unfortunate notation, but it's used everywhere, so you might as well just get used to it instead of fighting it, that we use an uppercase letter typically to represent the random variable as a conceptual entity. So if we say capital X, we're talking about a die roll that we could have. When we use a lowercase x or a lowercase y or a lowercase letter of any sort, we tend to be talking about realized values of the random variable. So the x lowercase should be something that you should be able to plug a number into, where capital X is a conceptual random variable. It's a conceptual flip of a coin. It's a conceptual roll of a die. Lowercase x is 1 or 2 or 3 or 0. Okay, and it's slightly unfortunate notation. It takes a little bit of getting used to, but I think for everyone who works in statistics or probability, they've gotten used to it, and everyone does it, so you might as well do it too. Let's go over an example of constructing a probability mass function. Let's take the simplest possible example, a coin flip. So let's let x be the result of a coin flip where 0 represents tails and 1 would represent a head. So we want the function, and let's assume that the coin is fair. So we want a function that maps 0 to 1/2 and 1 to 1/2. And there's infinitely many ways you could write down that function. Well, we're going to pick one. Here we write it as 1/2 raised to the power x times 1/2 raised to the power 1 minus x. And notice that if you plug in x equals 0, you get 1/2. And if you plug in x equals 1, you also get 1/2. Now let's go to a slightly more complicated example where we assume that the coin is potentially biased, i.e. that it's not fair. So let's let theta be the probability of a head, in this case expressed as a proportion between 0 and 1. So just as an example, imagine if theta was 0.3 instead of 1/2, then we would think that the probability of a head is 0.3 and the probability of a tail is 0.7. But let's leave it as theta for right now. So we want a function that says probability of a 0 is 1 minus theta and the probability of a 1 is theta. And then we see our function here, theta to the x, 1 minus theta to the 1 minus x exactly satisfies these properties. This is another common notation in the field of statistics that Greek letters like theta represent things that we don't know that we would like to know. So imagine if you had a coin and you didn't know whether or not it was fair, we would represent that unknown probability of a head as theta. So I want to give you a sense of where we're going. In this case, the probability mass function is the entity that governs the population of coin flips. And so if we wanted to know theta, we're going to collect data to estimate it and then to evaluate the uncertainty in that estimate. And the way we're going to evaluate uncertainty in that estimate is using this probability distribution. So all the probability distributions we're going to talk about are conceptual models of populations, and they are the entities that are going to tie our data to the population. So at any rate, right now this may sound a little heady, and we'll discuss this in much more detail throughout the entire class, but the one rule I want you to remember right now is that unknown things that we want to know, like in this case what would be the probability of a head, are generally denoted in Greek letters. These are called parameters usually. I also want to note one other thing. Why is it among all the possible ways that we could have written out this probability mass function did we choose theta to the x, 1 minus theta to the 1 minus x? There's lots of different ways we could have done this. You can try and figure some of them out yourself. Well, it turns out and we'll discuss this at length, that in probability, multiplying is very useful. And so we want probability mass functions that make multiplication very easy. So if we take things and raise them to powers, then multiplying becomes easy. And that's a general rule. And you'll see later on why this is the case. But at any rate, this is why we choose this particular form of the probability mass function when you could write it so many different ways. But I want to say people have thought about this a lot, and this is definitely the most useful way to write out this particular probability mass function. So consider again the unfair coin. Our probability mass function satisfies p of 0 equals 1 minus theta and p of 1 equals theta. Let's just go through the exercise to prove to ourselves that this is in fact a probability mass function. It's greater than 0 because it's 1 minus theta for 0 and theta for 1, and in this case theta is between 0 and 1. So it's going to be greater than 0 for x equals 0 and 1. And then the sum of the probabilities, probability of 0 plus the probability of 1, in this case is theta plus 1 minus theta, which is 1. So it satisfies the two rules that probability mass functions have to satisfy. So that covers our principal entity that we're going to use to model discrete random variables, probability mass functions. So now we need to cover our principal entity that we're going to use to model continuous random variables, which are called probability density functions. So probability density functions are abbreviated PDF, by the way. So it stands for probability density function, not portable document format, which is what lots of people think of as PDFs. But in statistics, no one thinks of PDFs that way. I want you to remember one very important rule, and I put it in italics just to make sure everyone remembers it. And by the end of the course, this will be second nature to you, but if you haven't seen it before, it might seem a little odd. But the way that probability density functions work are that areas under probability density functions correspond to probabilities for the random variable. And there's definitely one undisputed king of all PDFs, and that is the so-called bell curve. So if you ever wondered what a bell curve was, if you hear it talked about a lot, the so-called normal density function, you might wonder what in the world is a bell curve accomplishing? Well, areas under bell curves correspond to probabilities. So if you're modeling something as if the population it belongs to follows a bell curve, then you are saying that probabilities associated with that random variable are governed by areas under that bell curve. So that's just one example of a PDF. There's lots of different kinds of PDFs. So just like probability mass functions have to follow two rules, probability density functions have to follow two rules to be a valid probability density function. They have to be positive for all the possible values that the random variable can take. That's called the support usually. And their integral has to be 1. I would also say a small point here. We define probability density functions as if they operate on the whole real line. So even if your random variable can only take values, say, between 0 and 2, like we talked about earlier with the pencil experiment, even if that's the case, we define the probability density function as 0 below 0 and 0 above 2 so that there's no associated probability, but we've defined the probability on the whole real line so that we define its integral from minus infinity to plus infinity. And I think in this class we tend to be a little bit fuzzy about sometimes operate on minus infinity to plus infinity, and other times we'll just write out 0 to 2, discarding all the area where the function is 0, and I hope from the context it'll be clear what we're doing. This final property, property 2 here, that the integral over the whole real line of the probability density function has to be 1, is simply again saying that the random variable has to take some value, that it has to be in some interval in the whole real line. Let's go through a specific example of a PDF, and let's put it in a context. So let's assume that the time in years from diagnosis until death with a specific kind of cancer follows the density that looks like this. F of x equals e to the negative x over 5 divided by 5 for x greater than 0. The greater than 0 being contextually clear because you can't have negative time from diagnosis, and the person is presumably alive at the time of diagnosis. So this is a very restricted example of a density that's commonly used in these sorts of analyses of things like survival times. It's called the exponential density function. And again, here you see that we have f of x written as e to the negative x over 5 for x bigger than 0, and 0 otherwise. Like I talked about in the previous slide, we often just ditch that 0 and just talk about f of x being the kernel of the function and just either explicitly write, or sometimes we'll fudge a little bit that x has to be greater than 0 if it's clear from the context that that has to be the case. In this case, it would be clear from the context. Is this a valid density? Could we model survival time after diagnosis with this density? Well, first of all, we know that the function is positive because e raised to any power is always positive. And then let's just check whether or not it integrates to 1. So we want the integral from minus infinity to plus infinity, but like we said, all of the meat of the distribution starts at 0 and goes to infinity. So let's just say the integral from 0 to infinity, f of x dx, is, in this case, the antiderivative is negative e to the negative x over 5, which when evaluated from 0 to infinity yields 1. Let's go through an example of using this probability density function to assign probabilities. So imagine if we were to model this population as if it followed this specific exponential probability distribution, and imagine if someone asked us the question, what's the probability that a randomly selected person from this population survived more than 6 years? So if x is the conceptual value that a random person takes, we want to know what's the probability that x is greater than or equal to 6, as represented by this probability statement. Remember again the golden rule for probability density functions that areas under the curve correspond to probabilities. So if we want the probability x is greater than 6, we want the integral from 6 to infinity of the probability density function. And you can go through the calculus here to get that that works out to be about 30%. In the statistical programming language R, you can do this automatically. It just does the integral for you. It uses a numerical approximation, and you just write px6 for the fact that we want the probability of 6 or larger. 1/5 represents this parameter 5 that you see in the exponential distribution. Lower dot tail equals false means that we want the probability of being larger than 6 rather than the probability of being smaller than 6. So lower dot tail equals true would give you 6 or smaller. Lower dot tail equals false will give you 6 or larger. I want to elaborate on that point, by the way. For a continuous random variable, the probability that it takes any specific value is in fact 0. Now that seems strange, but it's true. So remember, areas under probability density functions correspond to probabilities. So what's the area of a line? It's 0. Now you might say, well, that doesn't make any sense at all. Specific values have to take probabilities because we see specific values when we actually observe variables. The point is that our probability density function is a model, and it is defined on continuous random variables. Continuous means measured to infinite precision. And so when we observe things, we never measure them to infinite precision. We measure them to finite precision. And probability density functions are perfectly happy with saying the probability that x is 6.01 to 5.99 and assigning a perfectly valid probability to that. But the probability that it's exactly 6 is 0. Because remember, exactly 6 means 6.0 followed by an infinite trail of zeros, or 5.99 followed by an infinite trail of 9s. Either way, that's the idea behind what probability density functions are getting at. They're modeling truly continuous random variables. So just remember that when we observe data, we of course measure them with finite precision, but our continuous model is exactly that. It's a model. We find it far more useful in many circumstances to model random variables as if they were truly continuous than to account for all the potential specific values they could take. So in this specific example, a person will only measure how long they survive to the year, maybe to the month, maybe to the day, maybe to the hour, to the minute, to the second, but probably not much further than that. And so we're only going to measure to finite precision. Nonetheless, it still is much more useful to model that as if it was continuous because we don't want to have to assign probabilities to every single value. We want to assign a general function. And that's why continuous random variables are so intrinsically useful. So the belabored point I'm trying to make about this, by the way, is that whether or not you write probability x being greater than or equal to 6 or the probability of x being strictly greater than 6, in this case, doesn't change this calculation whatsoever. You get 0.301 either way. And so it also doesn't make a difference in the probability exponential for the R example. It doesn't matter whether you specify lower tail or upper tail, whether you're thinking about whether or not that includes 6, it doesn't care about that. However, for discrete random variables, it makes a big difference, right? Because specific values have actual probabilities assigned to it. So a die can take the value 1, 2, 3, 4, 5, or 6. So in R, if you're using these probability functions, so px are probabilities from the exponential distribution, p binom are probability from the binomial distribution, p Poisson or POIS for Poisson is probabilities from the Poisson distribution, p gamma probabilities from the gamma distribution. R follows that rule pretty neatly. If it's a discrete random variable, you have to be careful about whether or not it's including the 6. For a continuous random variable, you can be very sloppy about it. So here I'm just depicting the area that we're calculating. This gray area is the survival time from 6 to infinity. This is simply the integral that we're actually calculating. And I'll put the R code to generate exactly this figure in the files for the course. So in that specific example, we looked at what's the probability that the random variable was larger than 6. But we might want to look at what's the probability the random variable is larger than 7, or smaller than 6, or smaller than 5, or smaller than 4.3, or so on. So if you take a random variable, you could construct a function that when you plug in a value, returns the probability that the random variable is less than that value. And you could construct a function that when you plug in a value, returns the probability that the random variable is larger than that value. And these things are so inherently useful that we give them names. So the cumulative distribution function, CDF, is simply a function that takes any specific value and returns the probability that the random variable is less than that value. And again, if it's continuous, it doesn't matter whether it's less than and equal to or less than, but the cumulative distribution function is defined for both continuous and discrete random variables, so let's be specific and say that it's less than or equal to. The survival function is the opposite, namely that it is exactly the probability that a random variable is larger than any specific value. So if you plug in x into the survival function, it returns the probability that the random variable is larger than x. So if on our previous slide, this figure, imagine if on the horizontal axis, instead of looking at 6, I was looking at some arbitrary value x, the gray area would be s of x, and the white area to the left of x and to the vertical axis would be f of x. Notice in this case that f is the probability of being less than or equal to x, s is the probability of being strictly greater than x, so that s of x and f of x have to add up to 1 because they're probabilities of complementary events. Probability x is less than or equal to x, and the probability x is strictly greater than x. So if you've calculated the cumulative distribution function, you have also calculated the survival function because all you have to do is 1 minus it. Conversely, if you've calculated the survival function, then you've calculated the cumulative distribution function. Next, we'll just go through our previous example and calculate exactly the survival function and the CDF. Let's actually go through an example of calculating the survival function and cumulative distribution function just from the exponential density that we considered before. Let's calculate the survival function first. So recall the survival function is the probability that the random variable is strictly greater than the value lowercase x. So further recall that to calculate probabilities, we need to calculate areas under the probability density function. In this case, we want the probability of being x or larger, so let's take the integral from x to infinity of our probability density function. Here I use the dummy variable t for integration. The integral or the antiderivative of e to the minus t over 5 divided by 5 is just negative e to the negative t over 5. We want to evaluate that from x, which yields the value e to the minus x over 5, and then subtract off the value as it limits to infinity, which is 0, so we just wind up with e to the minus x over 5. Now we could also go through the example of calculating the cumulative distribution function, which would, instead of calculating the integral from x to infinity, we would just be calculating the integral from 0 up to x. But because we've already calculated the survival function, we know that it's 1 minus the survival function, so it's 1 minus e to the minus x over 5. So the cumulative distribution function is the integral from minus infinity to x of the probability density function. Again, here we're just doing 0 because the integral from minus infinity to 0 is 0. And so we can just apply the fundamental theorem of calculus and note that the derivative of the CDF is exactly the density again. So if we take, just to go through our specific example, 1 minus e to the negative x over 5 and take the derivative of that, we get exactly e to the negative x over 5 divided by 5. So we get the PDF back. So derivatives of the cumulative distribution function exactly yield the probability density function back. Quantiles are properties of distributions or density functions equivalently. When I talk about a distribution or density in general, I'll just maybe say the word distribution. So if I want to talk about the bell curve or the associated distribution, I'll just talk about the Gaussian distribution or the normal distribution and so on. And then when we're talking about the mathematics, I'll be more specific. The alphath quantile of a distribution is the point so that the probability of being less than that point is exactly alpha. So we want, if x of alpha is the alphath quantile of the distribution, we want the probability of being less than or equal to x sub alpha to be exactly alpha. So let's just take as a specific example, if alpha was 0.25, x sub 0.25 is that point such that the probability of being less than it is 25%. So for example, in our cancer survival example, the 0.25th quantile of that distribution is the time of survival so that 25% of the people survive less than that time. The percentile is merely the quantile expressed as a percent, so the 25th percentile is the 0.25th quantile. And then the median, the population median, is exactly the 50th percentile. Let's just go through these concepts again with our density that we've been looking at, this exponential density. Suppose we wanted to find the 25th percentile of the exponential survival distribution. What we want is to find the point x on the horizontal axis so that the white area to the left of it is 0.25. So let's actually go through this calculation. In order to find the point so that the area to the left of it is 0.25, we just want to solve the equation 0.25 equals f of x. Well, recall in this problem a couple of slides ago, we solved that f of x is 1 minus e to the negative x over 5. And if you just simply solve that for x, we wind up with the solution x equals minus log 0.75 times 5, which is about 1.44. How is that 1.44 interpreted? About 25% of the subjects from this population lived less than 1.44 years. You can get quantiles directly from R by the Q function, Qx in this case, because we're talking about the exponential PDF. So Qx gives you quantiles from the exponential PDF. Px gives you survival or CDF probabilities from the exponential. And dx gives you the density itself, and that rule R follows for most of the common distributions. The median, to remind you, is the 0.5th quantile, the 50th percentile. And the quantile that we just figured out, the 0.25th quantile, is generally called the lower quartile. And you might have said, well, I've heard of the median before. Maybe I've heard of what a lower quartile is before. And what those things are, to me, is that they're the middle of the data, or the point in the data so that 50% of the observations are lower than it. Or the lower quartile is that point in the data so that 25% of the observations are below it. What in the world is Brian talking about at this point? So when we talk about the median that we're discussing in this lecture, we're talking about the population median. And when you collect data and you take a sample median, that's an estimator of something, so we should talk about what that's an estimator of, right? It's an estimator, it has to have an estimand. In the same way, if we take a sample mean of data, that's an estimator of something, it has to have an estimand. And so what we're talking about in this lecture is one way to construct estimands of these quantities. In this case, the median, if you take the sample median, it is hopefully trying to estimate the population median, that point in the population, so that the probability of being less than it is 50%. And you'll find in this class that there's this simple rule. Sample things tend to estimate population things. So sample medians estimate population medians, sample variances estimate population variances, sample means estimate population means, and so on. And what we're going to see is this probability modeling and the associated assumptions. These are the things that connect our data to the population so that we can actually have estimands. If we didn't go through this exercise, we would be able to take a median, but that would just be an entity in the sample. The whole point of probability modeling is then it connects your sample to this population so that your sample median now has a population median that it's trying to estimate. Now, and this is kind of a very difficult concept. I think the sample median is a very easy concept. It's saying, you have a list of observations, take the middle one after you order them. The population median is a much more difficult concept. It's saying, I have described a population via this distribution, and this distribution has a point so that 50% of observations lie below it, and that's the population median. And I think it's a good idea whenever you're talking in this class to put the word population or sample in front of it to remind yourself. Now, people who work in statistics do this so much that they just kind of forget about these distinctions, even though they know them. They just forget about them because they become sort of second nature. But when you're first learning this, it seems quite odd. And I also want to mention, the sample median is the well-defined quantity that doesn't require tons of assumptions. It's the probability modeling that's the delicate part that requires assumptions. So if you're going to say that the sample median estimates the population medians, well, there's assumptions that need to be taken into account for that to be true. And especially if you want to do inference with your sample median or evaluate its uncertainty. And that's basically what we're going to spend nearly all of this class discussing, is how are we going to connect these probability and population concepts to sample data. Thanks, recruits. This was Mathematical Biostatistics Boot Camp Lecture 2. In the next lecture, we're going to expand on probability modeling and defining characteristics of probabilities. And I look forward to seeing you.